Alright, before we get into the heart of this, let's be crystal clear. This video is for informational and educational purposes. I'm here to share my research and insights, but your career is one of the biggest decisions you'll ever make. So treat this as a powerful starting point, but always do your own deep dive research. Do you ever get that feeling in the pit of your stomach? That little bit of anxiety when you see another headline about AI taking over, or a new robot that can do a human's job but faster and for cheaper? You're not crazy for feeling that way. We're living through the single greatest economic shift since the Industrial Revolution. The World Economic Forum predicts that by 2025, 85 million jobs could be displaced by machines. Think about that. That's like the entire population of California and Texas combined, suddenly finding their skills are obsolete. It's a terrifying thought. But here's what they don't put in the headlines. In that very same report, they predict that 97 million new roles will be created. New jobs. More specialized, more technical, and frankly, more valuable jobs. The question is no longer if the robots are coming. They're already here. The real question, the one that will define your financial future for the next 20 years is this. Are you going to be the person replaced by the machine? Or are you going to be the person who designs, builds, and controls the machine? Because that's what this is all about. We're not here to fearmonger about the future. We are here to give you a roadmap to owning it. Over the next few minutes, we are going to pull back the curtain on one of the most misunderstood, yet explosive career paths in the United States today: automation engineering. This isn't just about factory robots bolting cars together anymore. This is about the invisible systems that run our world. And I'm going to give you the real story. We will break down exactly what an automation engineer does day to day, the good, the bad, and the surprisingly creative. We're going to talk about the money. Not the inflated numbers you see on some recruiting website, but the real salaries people are earning right now in states like North Carolina, Arizona, and Michigan. We will lay out the exact skills, the programming languages, the software, the hands-on knowledge that companies are desperately searching for as we head toward 2026. And by the end of this video, you will have a clear, honest answer to the most important question. Is this the right career for you? Is this a path that aligns with your skills, your interests, and your ambitions? Because the truth is, this revolution is happening in places you'd never expect. It's in the Amazon warehouse that gets a package to your door in under 24 hours. It's in the software that tests the banking app on your phone. It's in the vertical farms that grow lettuce with 95% less water. It's everywhere. And the people who can orchestrate this complex dance between hardware, software, and human ingenuity are not just surviving this economic shift, they are leading it. They are becoming the architects of the new American economy. So if you're ready to stop worrying about the future and start building it, you are in the exactly right place. Let's start by demolishing the biggest myth about what this job actually is. When you hear the words automation engineer, what's the first image that pops into your head? For most people, it's probably a scene straight out of a sci-fi movie. A lone genius in a lab coat, surrounded by gleaming robotic arms, maniacally laughing as they program a machine that will eventually make 1,000 factory workers obsolete. It's the classic Hollywood-fueled narrative. Automation equals robots, and robots equal job killers. This single pervasive myth is the biggest barrier to understanding one of the most critical and opportunity-rich careers of the next decade. And it is completely fundamentally wrong. Thinking an automation engineer just builds robots is like thinking a master chef just knows how to chop vegetables. It misses the entire point. The robot, the conveyor belt, the sensor, those are just ingredients. The automation engineer isn't the line cook. They are the executive chef, designing the entire kitchen, writing the cookbook, and orchestrating the symphony of 1,000 moving parts to create a perfect, repeatable result every single time. They aren't replacing the human. They are elevating the human, removing the drudgery, the danger, and the monotony, so people can focus on what people do best: thinking, creating, and improving. To really get this, let's step inside a real American factory. Not a futuristic one, but one from just a few years ago. Let's meet a guy named Mark. Mark is a great maintenance technician, one of the best. His day is a frantic blur of non-stop firefighting. At 8 a.m., a bottling line conveyor jams. He sprints over, wrenches in hand, and spends 45 minutes clearing a jam caused by a slightly misshapen bottle. At 10 a.m., a pressure valve on a mixing tank starts fluctuating. He spends the next hour tweaking it by hand, watching a needle on a physical gauge, trying to find the sweet spot while the entire production line waits. After lunch, a labeling machine starts misapplying labels, sticking them crooked on every 10th product. Mark has to shut it down, manually recalibrate the sensors, run a dozen test products, and hope he got it right. His entire day is reactive. He's a hero for sure, but he's a hero patching holes on a sinking ship. He's exhausted, the company is losing money on downtime, and the quality of the product depends entirely on how tired Mark is on any given Tuesday. This isn't efficient. It's not sustainable. And frankly, it's a waste of Mark's talent. Now let's bring in an automation engineer. Let's call her Priya. Priya doesn't walk in and say, "Let's replace Mark with a robot." That's the myth. Instead, she walks the floor for a week with a notepad and a laptop, and she watches. She talks to Mark. She talks to the operators. She doesn't just see individual machines. She sees a system. She sees a flow of information, or more accurately, a lack thereof. She sees data that's being created but is just evaporating into thin air. Her first target is that jamming conveyor belt. She doesn't just build a bigger, stronger robot to unjam it. She installs a series of smart sensors and a vision system. A high-speed camera connected to a small computer. This system inspects every single bottle before it gets to the line. If it detects a bottle that's even a millimeter out of spec, a tiny puff of air gently nudges it onto a rejection chute. The jam never happens. The line never stops. Mark doesn't have to sprint across the factory floor anymore. Next, she looks at the mixing tank. That analog pressure gauge Mark was staring at? Priya replaces it with a digital sensor that feeds data 100 times a second into something called a PLC, a programmable logic controller. Think of the PLC as the brain of the operation. It's a rugged industrial computer that speaks the language of machines. Priya writes a small program for that PLC. The program says, "Continuously monitor this pressure. If it starts to drop, automatically open this valve just a tiny bit. If it gets too high, close it a tiny bit." The PLC now does the tedious job of watching the needle, making microscopic adjustments faster and more accurately than any human ever could. It holds the pressure perfectly steady all day, every day. Product quality becomes consistent and predictable. Then she tackles the labeling machine. She connects its sensors to the same PLC. She installs what's called an HMI, a human-machine interface. This is basically a tough, industrial-grade touchscreen tablet mounted on the machine. Instead of Mark having to manually tweak screws and gears, the operator can now see a graphical display of the machine. They see real-time data on label alignment. If it drifts, an alarm pops up on the screen, showing them exactly which setting to adjust using a simple slider on the touchscreen. The guesswork is gone. What Priya has done is build a nervous system for the factory. The sensors are the nerve endings, feeling pressure, seeing shapes, and sensing position. The PLCs are the local brains, making instantaneous decisions. And the HMI is the face, allowing humans to intelligently communicate with the system. She might even integrate a robot, the muscle, to expertly palletize the finished products at the end of the line, a backbreaking and repetitive job that often leads to worker injury. The robot isn't the star of the show. It's just one highly specialized actor in a much larger play that Priya has written and directed. And the most powerful part? All of this data, the number of rejected bottles, the pressure fluctuations in the tank, the label alignment statistics, is no longer evaporating. It's being collected, stored, and analyzed. Priya can now build dashboards that show trends over time. She might discover that all the misshapen bottles are coming from a single supplier, or that a specific valve is starting to show signs of wear long before it fails. The factory is no longer just running. It's learning. It's getting smarter. So what happens to Mark, our hero technician? Is he out of a job? Absolutely not. His job has been upgraded. He's no longer a firefighter running from one crisis to the next. He's now a systems analyst. He spends his mornings looking at the data dashboards Priya built. He sees that the pressure valve on tank 3 is requiring more and more adjustments from the PLC. He schedules a predictive maintenance check, replacing a $50 gasket a week before it would have failed and shut down the entire plant for a day, saving the company $100,000. He's using his deep mechanical knowledge, but now it's amplified by data. He's more valuable than ever, and his work is infinitely more rewarding. This is the reality of automation engineering. It's not about replacing humans. It's about creating systems that are safer, more efficient, and produce higher quality results, empowering people like Mark to work smarter, not harder. And it's not just in factories. This same thinking is being applied everywhere. In the massive Amazon fulfillment centers, automation engineers design the symphony of robots and conveyors that get your package to your door in 24 hours. In pharmaceutical plants, they build systems that guarantee every single pill has the exact right dosage, with a level of precision that saves lives. They design the control systems for the nation's power grid, the water treatment plants in your city, the baggage handling systems at the airport, and even the complex animatronics and ride systems at a Disney theme park. They are the ultimate systems thinkers, the modern-day wizards who blend mechanical engineering, electrical engineering, and computer science into a single powerful discipline. They are the ones building the invisible infrastructure of the modern world, making everything we rely on work better, faster, and more reliably. They aren't just building robots, they are building the future, one intelligent system at a time. The real question isn't, will a robot take my job? But, how can we design a system to make that job better? And the person who answers that question is the automation engineer. So we've busted the myth. We know they're not just robot builders. They're the conductors of an incredibly complex orchestra. But what does it actually take to become one? What kind of person thrives in this role? It's probably not who you think, and the answer might surprise you because it's less about being a coding genius and more about possessing a specific, almost forgotten way of thinking. So, what is this forgotten way of thinking? It's the mindset of the master tinkerer. It's the soul of a mechanic. It's the person who, as a kid, didn't just play with Legos, they built intricate machines with them. It's the person who took apart the family VCR, not out of malice, but out of an insatiable burning curiosity to understand how the gears, levers, and electronics all work together to play a movie. It's about seeing the world not as a collection of static objects, but as a series of interconnected systems. You don't just see a car. You see an engine, a transmission, a drivetrain, and an electrical system all performing a delicate high-speed ballet. You don't just see a coffee maker. You see a heating element, a water pump, a timer, and a series of valves all executing a precise sequence. This is the core of an automation engineer. It's a deep fundamental desire to understand the how and the why of a process, and then the creative spark to ask, how can I make this better, faster, and more reliable without a human touching it? It's a blend of a detective's logic and an inventor's imagination. You have to be able to look at a massive, clanking, 100-yard-long assembly line and mentally deconstruct it into its smallest logical pieces. Then you have to be able to put it all back together, not with your hands but with code, wires, and sensors. So, with that mindset as the foundation, what are the actual hard skills you need to build on top of it? What's in the toolbox of a modern automation engineer? Let's break down the big three pillars. First, and arguably the most important, is understanding programmable logic controllers, or PLCs. Forget what that fancy name sounds like. A PLC is simply a small, ruggedized industrial computer. It's the brain of almost every automated process on the planet. Your car was assembled by robots controlled by PLCs. The water you drink was purified and pumped to your house by a system controlled by PLCs. The box that Amazon delivered this morning was sorted, scanned, and routed through a massive warehouse by a symphony of PLCs. They are everywhere. Learning to program them is non-negotiable. Now, this isn't like programming a website or a mobile app. The most common language, called ladder logic, literally looks like an electrical schematic, a ladder diagram. It was designed so that electricians and maintenance technicians back in the 70s could understand it without needing a computer science degree. It's a language of logic, of inputs and outputs. If this sensor sees a box, and this light curtain is clear, then fire this pneumatic piston to push the box onto that conveyor. It's a very direct cause-and-effect way of thinking. The dominant players in the US are Rockwell Automation, with their Allen Bradley brand, and Siemens. Getting proficient in the software for one or both of these is like learning to speak the native language of the factory floor. The second pillar is robotics. This is the brawn to the PLC's brain. When you think of automation, you probably picture a giant 6-axis robotic arm, gracefully welding a car frame or precisely placing a tiny microchip. And you'd be right. Understanding how to integrate, program, and troubleshoot these robots is a huge part of the job. We're talking about industry giants like Fanuc with their iconic yellow arms, Kuka and Orange ABB, and Universal Robots, who are pioneers in collaborative robots, or cobots, that can work safely alongside humans. And here's the secret. Programming a robot's basic movement is often the easy part. They have intuitive teach pendants, which are essentially ruggedized tablets with joysticks that let you manually move the arm to a position and save it as a point. The real magic, the real engineering, is in the integration. How does the robot know a part is ready to be picked up? That's a signal from a PLC. How does it know it picked the part up correctly? It gets feedback from a sensor on its gripper. What happens if it drops the part? It needs to execute a fault routine, maybe send an alert to an operator and try again. You're not just a robot programmer. You are the choreographer of a dance between the robot, the controllers, the sensors, and the physical parts moving down the line. The third pillar is the one that ties it all together: HMI and SCADA. Another set of intimidating acronyms, but again, simple concepts. HMI stands for Human-Machine Interface. It's the screen on the factory floor. It's the operator's window into the soul of the machine. As an automation engineer, you design these screens. You decide which buttons the operator needs, what alarms should pop up, what data is most important for them to see at a glance. A good HMI is intuitive, clean, and allows someone to run a multi-million-dollar piece of equipment with confidence. SCADA, which stands for Supervisory Control and Data Acquisition, is like the HMI's big brother. It's a higher-level system that doesn't just look at one machine, it looks at the entire plant, or even multiple plants. It's the control room you see in movies, with dozens of screens showing the status of everything in real time. It collects or acquires massive amounts of data: temperatures, pressures, speeds, counts, faults, and presents it in a way that allows managers to make smart decisions. Building these systems requires you to think about the user experience, data visualization, and even a bit of networking and database management. You're building the dashboard for the entire manufacturing enterprise. So you're nodding along. You're the kid who took apart the VCR. You're fascinated by PLCs, robots, and big-picture control systems. The next logical question is, how do I actually get these skills? What's the path? The good news is there isn't just one. There are several, and they cater to different life stages and learning styles. The most traditional path is a 4-year university degree, a Bachelor of Science in Mechanical Engineering, Electrical Engineering, or better yet mechatronics, which is a fantastic blend of all of these disciplines. This route gives you an incredibly strong theoretical foundation. You'll understand the physics behind the motion, the deep theory behind control loops, and the advanced mathematics that govern complex systems. The downside? Sometimes these programs can be light on hands-on experience with the specific brands, the Allen Bradleys and Fanucs, that companies are actually using. You might graduate knowing the theory of a robot's kinematics but having never actually jogged a real one. That's why the second path is gaining so much respect and traction. The 2-year associate's degree from a community or technical college. Look for programs with names like automation technology, mechatronics, or industrial maintenance. These programs are often laser-focused on employable skills. They build labs filled with the exact same PLCs, robots, and motor controls that are used in the factories down the street. Their instructors are often industry veterans. You will spend less time on abstract calculus and more time wiring a control panel and troubleshooting a faulty sensor. For many, this is a faster, more affordable, and more direct path to a fantastic job as an automation technician or specialist, where you can then work your way up to an engineering role. Companies are desperate for people with these hands-on skills. The third path is for the career changers. Maybe you're an electrician who wants to get into programming, or a mechanic who sees the writing on the wall, or maybe you're in a completely unrelated field and want to change. This is the trade school and certification route. You can find intensive, week-long or month-long boot camps that focus on one specific skill, like Rockwell PLC programming or Fanuc robot maintenance. These are not cheap, but they are a direct injection of a specific in-demand skill. You won't get the broad theoretical base of a university degree, but you will walk out with a tangible, marketable skill and a certificate to prove it. This is the Special Forces approach: fast, targeted, and intense. Finally, let's not forget the fourth path, the one that many of the best in the field have taken: the on-the-job learner. This is the person who starts as a machine operator, shows a knack for troubleshooting, gets moved into maintenance, and just soaks up knowledge like a sponge. They stay late with the engineers, they ask questions, they read manuals in their spare time, and they convince their boss to send them to a training class. They build their career from the ground up, earning their expertise through grease, sweat, and an unquenchable curiosity. This path proves that the tinkerer's mindset is truly the most important asset, because with it, you can take any starting point and build a remarkable career. Each of these paths is valid. Each can lead to a successful, high-paying role as an automation engineer. The question you have to ask yourself isn't which one is best, but which one is best for me right now? Because once you have the skills, a whole new world of opportunity opens up. A world that pays incredibly well. But just how well? Let's talk numbers. Real numbers. From entry-level to seasoned expert, what can you actually expect to make in this field? The answer is probably a lot more than you think. Alright, let's pull back the curtain and talk about the numbers that really matter. The figures that turn a passion into a profession, and a job into a wealth-building machine. We're not talking about vague estimates. We're talking about the hard data, the pay stubs, the direct deposits that are redefining what it means to be a successful engineer in America today. Let's start at the beginning. You've just graduated, degree in hand, ready to take on the world. What does that first paycheck look like for an entry-level automation engineer? Forget the idea of ramen noodles and scraping by. The average starting salary for an automation engineer in the United States right now hovers between $75,000 and $95,000. Let that sink in. In many parts of the country, you are starting your career at a salary that takes other professions a decade to reach. This isn't just good for a first job money. This is aggressively pay down student loans, put a real down payment on a car, and actually start investing in your 20s money. Of course, this isn't a flat number. Location is a huge factor. A starting role in a high cost of living area like San Jose, California, or Boston, Massachusetts, could easily push you over the $100,000 mark right out of the gate. A similar role in the Midwest, say in Ohio or Indiana, might start closer to that $75,000 or $80,000 range, but your money goes significantly further. The industry also plays a massive role. A recent grad stepping into a highly regulated field like pharmaceuticals or aerospace will often see a higher initial offer than someone going into general manufacturing, simply because the stakes are higher and the required precision is non-negotiable. Now let's fast forward 5 to 7 years. You're no longer the new kid on the block. You've seen projects succeed, you've seen them fail, and you've learned critical lessons from both. You've developed a specialty. Maybe you're the go-to person for robotic arm integration, or perhaps you've mastered the complex world of Siemens and Rockwell PLC programming. This is the mid-career stage, and this is where the financial trajectory gets really exciting. At this point, you're looking at a base salary that has comfortably crossed into six figures. We're talking a range of $110,000 to $150,000 a year. And in high-demand markets or specialized niches, that number can climb even higher. This is the point where your financial life fundamentally changes. You're not just comfortable anymore. You're building serious wealth. This is the salary that buys a family home in a good school district. It's the salary that allows you to max out your 401k, invest in the stock market, and still take that amazing vacation you've been dreaming about. Think about it this way. The leap from entry-level to mid-career isn't just an incremental pay bump. It represents a shift in your value. You're no longer just executing tasks given to you. You're now designing systems, leading small teams, and solving complex problems that have a direct impact on a company's bottom line. You're the one preventing $1 million an hour production line from going down, and you are compensated accordingly. But we're not at the top yet. Not even close. Let's push forward another 10 years. You are now a seasoned expert, a veteran with 15, maybe 20 years of experience under your belt. You are a principal automation engineer, a controls architect, or maybe you've gone the consulting route and become a sought-after expert in your field. What do the numbers look like now? This is where we enter the territory that many people don't even realize is possible in an engineering career. We are talking about base salaries in the range of $175,000 to well over $250,000. Yes, you heard that right. A $250,000 salary for being an expert in making things run automatically. And that's just the base pay. At this level, total compensation is the real story. We're talking about significant annual bonuses that can be 20, 30, or even 50% of your base salary, tied to company performance or project success. We're talking about stock options or restricted stock units, RSUs, that give you a tangible piece of ownership in the company you're helping to build. For a senior engineer at a major tech company like Amazon, Google, or Tesla, or a cutting-edge biotech firm, it's not uncommon for their total compensation package with bonuses and stock to reach $300,000 for $100,000, or even more per year. These individuals are the masterminds. They are not just programming a single robot, they are designing the entire automated ecosystem for a new gigafactory. They are creating the software architecture for a nationwide network of distribution centers. They are solving problems so complex and so valuable that their compensation is a reflection of the tens of millions of dollars they save or generate for their employers. They have transcended being just an engineer. They are a strategic business asset. Now let's put this on a map, because where you live and work can dramatically alter these figures. Think of the US as having different salary zones for automation. First, you have the top-tier gold mines. This is Silicon Valley, Seattle, and the Boston-Cambridge area. Here, the concentration of tech, biotech, and high-level R&D creates a feeding frenzy for top talent. A senior engineer in San Jose might command a base of $220,000, but the cost of living is astronomical. The question isn't just how much you make, but how much you keep. Then you have the sweet spots. These are cities like Austin, Texas, Raleigh, North Carolina, Denver, Colorado, and Phoenix, Arizona. These are booming tech and manufacturing hubs with a significantly lower cost of living than the coastal giants. A salary of $150,000 in Austin can give you a lifestyle that might require $250,000 in the Bay Area. These cities represent a powerful combination of high opportunity and high quality of life. Finally, you have the industrial heartlands. Think Detroit, Michigan, Houston, Texas, and the manufacturing corridors of the Midwest. These areas have a deep-rooted need for automation in automotive, oil and gas, and heavy industry. While the absolute salary ceiling might not reach Silicon Valley levels, the demand is incredibly stable, the jobs are plentiful, and a strong six-figure salary provides an exceptionally comfortable life. The industry you choose is just as critical as your location. If you want to maximize your earning potential, look towards pharmaceuticals and biotechnology. The intense regulation and zero tolerance for error mean these companies pay a massive premium for automation experts who can deliver flawless, validated systems. Following closely behind is the tech sector. E-commerce giants, data centers, and semiconductor manufacturing are all in a perpetual arms race for efficiency and are willing to pay top dollar to win. Aerospace and defense also pay a premium for the extreme reliability their systems demand. But let's be clear, even in what some might consider less glamorous sectors like food and beverage or consumer goods manufacturing, the salaries are still fantastic. The sheer scale of these operations means that even a small efficiency gain can result in millions of dollars in savings, and the engineers who create those gains are rewarded handsomely. So when you add it all up, the strong starting salaries, the exponential mid-career growth, the astronomical potential at the expert level, and the lucrative bonuses and stock options, the financial picture becomes crystal clear. Automation engineering isn't just a job. It's not just a career. It is one of the most direct and reliable paths to financial independence available in the United States today. It's a field that rewards expertise with tangible, life-changing wealth. So we've established the pay is incredible, life-changing even. But let's be honest, money isn't everything. What does a day in the life of an automation engineer actually look like? Are you stuck in a dark factory staring at a screen for 10 hours? Or are you on the front lines of innovation building the future? The reality is a fascinating mix of both, and it's what we're breaking down next. So let's pull back the curtain. The first thing you need to understand is that automation engineer isn't one single job, it's a spectrum. On one end, you have the highly specialized code-heavy role, and on the other, you have the hands-on get-your-hands-greasy troubleshooter. Most roles, however, live somewhere in the messy, exciting middle. Let's break down the core pillars of this profession. The 4 fundamental roles you'll play, often all in the same week. First, you are the architect. This is the blank canvas phase. Imagine a company wants to launch a new product, say a revolutionary new type of battery. They have the battery design, but they need to figure out how to make 10,000 of them a day flawlessly. That's where you come in. You're not just thinking about one machine. You're designing an entire ecosystem. You'll sit down with mechanical engineers, electrical engineers, and process specialists. The conversation is a whirlwind of questions. How does the raw material get from the loading dock to the first station? What kind of robot arm can handle the delicate battery cells without crushing them? What sensors do we need to check for microscopic defects at 100 miles an hour? This is the cerebral part of the job. You'll spend hours in front of a computer, but you're not just staring at a screen. You're in a digital sandbox, a virtual world where you build the factory before a single bolt is turned. You're using software like AutoCAD Electrical to design the control panels, the brains of the operation. You're in SolidWorks, looking at a 3D model of the production line, simulating the ballet of a dozen robots to make sure they don't collide. And most importantly, you're laying the logical foundation. You're deciding on the programmable logic controller, or PLC, the industrial computer that will act as the central nervous system for the entire line. You're thinking about the human-machine interface, the HMI, the touchscreens that the operators will use to interact with this beast you're creating. This phase is pure problem solving. It's a high-stakes puzzle where every piece you place, every decision you make, has million-dollar consequences down the line. It requires immense foresight and a deep understanding of how things connect. from a tiny proximity sensor to the factory-wide network. Once the blueprint is approved, you transform into the second role, the builder. This is where the digital becomes physical, and it's often the most thrilling and chaotic phase. The components start arriving. Massive crates with 6-axis robots, shiny stainless steel conveyors, and spools of wire that could stretch for miles. Now you're on the factory floor. The air smells of new metal and freshly cut concrete. You're working with electricians and mechanics to bring your design to life. This isn't just supervising. You are deeply involved. You're overseeing the placement of sensors, ensuring the control panels are wired exactly to your schematics, and plugging in your laptop to establish the first handshake with a brand new robot. This is the commissioning phase. It's where you write the first lines of actual code that will make the machine move. You're not just programming, you're teaching. You teach a robot arm its precise path, a sequence of movements more graceful and exact than any human could perform thousands of times in a row. You write the PLC logic that says, when sensor A sees a part, and sensor B confirms its orientation, then start the conveyor, and tell the robot to pick it up. It's a language of pure logic. And let me tell you, the first time you press that cycle start button and watch 100 tons of steel, motors, and sensors execute the dance you choreographed in your mind, it's an incredible rush. It's a feeling of creation that few other professions can offer. Of course, it never works perfectly the first time. Wires are crossed, sensors are misaligned, and the code has bugs, which leads directly to your third, and perhaps most critical, identity. You become the detective. It's 3 a.m. The factory is humming, churning out product, but suddenly, a section of your line grinds to a halt. A red light flashes on a control panel, and an alarm blares. Every minute the line is down, the company is losing thousands of dollars. Your phone rings. Everyone is looking at you. This is where the real pressure kicks in. You are now a high-tech detective at a crime scene, and the victim is productivity. The culprit could be anything. Was it a faulty sensor? A loose wire? A mechanical jam? Or is there a subtle bug in the thousands of lines of code you wrote? A logical paradox that only appears under a specific rare condition? You plug your laptop into the PLC, your digital magnifying glass. You go online with the processor and watch the logic in real time. You see a sea of green representing true conditions, and you're looking for that one bit of code, that one rung of the ladder logic that isn't green when it should be. You're tracing the problem backward from the symptom. The robot didn't pick up the part. Why? Because the gripper didn't close. Why? Because the PLC never gave the command. Why? Because the part in position sensor never turned on. You race out to the floor, weaving through the machinery, and you find it. A tiny metal shaving is blocking the sensor, a 1 in a million fluke. You wipe it away, the sensor light comes on, and a moment later the entire line roars back to life. The relief and satisfaction in that moment are immense. You didn't just fix a machine. You were the hero who solved the case and saved the day. This is the adrenaline-fueled, problem-solving reality that separates a good automation engineer from a great one. Finally, after the line is built and the major bugs are squashed, you evolve into your fourth role, the optimizer. The system works, but it can always be better. Now your job is to hunt for inefficiency. You become obsessed with time. The process of welding two parts together takes 3.7 seconds. Is it possible to get it down to 3.5? You analyze the robot's motion path. You realize that by changing the angle of approach, you can shave off 100 milliseconds. By increasing the weld current just slightly, you can save another 100. It doesn't sound like much, but a 0.2-second improvement, repeated 10,000 times a day, adds up to over 33 minutes of extra production time daily. Over a year, that single tiny change could result in tens of thousands of extra products being made. You're a data scientist and a process guru rolled into one. You're analyzing cycle times, error rates, and sensor data to find patterns. You might notice that one specific machine faults out more than others. You dig in and discover a minor alignment issue that, when fixed, improves the entire line's uptime by 2%. You're not just maintaining the status quo. You are in a constant state of refinement, a quest for perfection. You're running experiments, tweaking variables, and implementing changes that have a direct, measurable impact on the company's bottom line. This is the part of the job that satisfies the deep-seated need to make things better, to leave a system more efficient and more robust than you found it. So, are you stuck in a dark factory staring at a screen? Sometimes, yes, during the intense design or late-night troubleshooting phases. But you're also on the floor, collaborating with a team of brilliant people, physically building and fine-tuning the future of manufacturing. You're an architect, a builder, a detective, and an optimizer. It's a dynamic cycle that ensures the job is never, ever boring. It's a career that demands both deep intellectual focus and practical, hands-on action. And the sheer variety of industries where you can apply these 4 roles is staggering, which opens up a world of possibilities for where your career can actually take you. Let's start with the most classic and perhaps the most visceral image of automation: manufacturing. When you think of a factory, you probably picture giant robotic arms, sparks flying, assembling a car on a production line. And you're not wrong. The automotive industry was one of the earliest and most aggressive adopters of automation, and it remains a massive employer of automation engineers. Here, you're not just programming a robot to weld a door panel. You're designing the entire symphony of the assembly line. You're ensuring that hundreds of robots, conveyors, sensors, and computer systems all work in perfect, high-speed harmony to transform a pile of sheet metal into a gleaming new vehicle in a matter of hours. You're solving problems of immense scale and complexity, where a single second of downtime can cost a company thousands of dollars. But it's not just cars. Think about the smartphone in your pocket or the laptop you're watching this on. The precision required to assemble those devices is mind-boggling. We're talking about placing microscopic components with tolerances thinner than a human hair, over and over again millions of times without a single error. A human hand simply can't do that. It takes an automation engineer to design, build, and maintain the sophisticated robotic systems that make modern electronics possible. You could be working on the lines that produce the next generation of processors, the screens for virtual reality headsets, or the batteries that power our increasingly electric world. It's a world of incredible precision and cutting-edge technology. Now let's shift gears from the massive and mechanical to the sterile and life-saving: pharmaceuticals and life sciences. This is an industry where the stakes are literally life and death. A mistake on a car assembly line might lead to a recall. A mistake in a pharmaceutical plant could be catastrophic. Because of this, the industry is heavily regulated by bodies like the FDA, with excruciatingly strict standards for purity, consistency, and documentation. And this is where automation becomes not just an efficiency tool, but a guardian of public health. As an automation engineer in this space, you might be designing a system that can fill thousands of vials with a life-saving vaccine, ensuring each one has the exact same dose, untouched by human hands in a completely sterile environment. You could be automating the complex process of bioreacting, where living cells are used to produce complex medicines, a process that requires precise control over temperature, pH, and nutrient levels for weeks on end. You could even be working in drug discovery, designing robotic systems that can test thousands of chemical compounds a day, dramatically accelerating the search for new cures. Every system you build has a direct impact on people's health and well-being. You're the one ensuring the medicine your grandmother takes is safe and effective. It's a field that offers not just a technical challenge, but a profound sense of purpose. But let's come back to something we all experience every single day: the magic of e-commerce. You click buy now on a product, and a day or two later, a box appears on your doorstep. How does that happen? It's not elves. It's an astonishingly complex and highly automated logistics network. And automation engineers are the wizards behind that curtain. Step inside a modern Amazon or Walmart fulfillment center, and you've entered the world they built. It's a city of robots. You have autonomous mobile robots, or AMRs, that look like giant Roombas, zipping around the warehouse floor, lifting and moving entire shelves of products to human pickers. You have high-speed conveyor systems with barcode scanners and automated diverters that sort millions of packages a day, routing them to the correct truck with breathtaking speed and accuracy. As an automation engineer in logistics, you're solving a giant, real-world puzzle. How do you optimize the flow of millions of different items in a 10 million square foot building? How do you design a sorting system that can handle the insane volume of Black Friday without breaking a sweat? You're using computer vision to identify products, machine learning to predict demand and position inventory, and robotics to do the heavy lifting. And it doesn't stop at the warehouse. Companies are pouring billions into automating the last mile of delivery with drones and sidewalk robots. This industry is expanding at a breakneck pace, and it is fundamentally built on the back of automation. Now for the industries that push the absolute limits of technology: aerospace and defense. When you're building a passenger jet or a rocket that sends humans to space, good enough isn't good enough. You need absolute, verifiable perfection. Here, automation engineers design systems for tasks that demand a level of precision and repeatability that is simply beyond human capability. Think about drilling thousands of holes in an aircraft wing with perfect placement and depth every single time. Or using laser-guided robotic systems to lay down carbon fiber composites to create structures that are both incredibly strong and incredibly light. In the defense sector, you're working on the bleeding edge. This could mean developing the control systems for unmanned aerial vehicles, or drones, that perform reconnaissance or deliver supplies in dangerous environments. It could mean designing automated manufacturing cells to produce sensitive military hardware with maximum security and quality control. This is a field for those who are fascinated by complex machines and thrive in high-stakes environments where failure is not an option. It's where engineering meets science fiction, and the applications don't stop there. Think about the food and beverage industry. Every can of soda, every bag of chips, every perfectly formed cookie that comes out identical to the last one is a product of automation. Automation engineers design the high-speed bottling lines, the robotic packaging systems, and the process controls that ensure food safety and consistency on a massive scale. Or consider the energy sector. We're talking about automating the controls for a city's power grid, developing the robotic systems that maintain wind turbines hundreds of feet in the air, or managing the complex valve and pipeline systems that transport oil and gas across the country. These are the invisible systems that power our modern lives, and they're all designed and maintained by automation engineers. So the opportunities are everywhere. But why? Why are all these diverse, powerful industries so hungry for this specific skill set? The demand isn't random. It's driven by a few fundamental forces that are reshaping our entire economy. First is the relentless pursuit of efficiency and productivity. In a competitive global market, every penny counts. Companies need to produce more, faster, and with fewer resources. An automated system can work 24 hours a day, 7 days a week, without breaks, vacations, or sick days. It can perform tasks at a speed and consistency that a human can't match. By automating a process, a company can slash its production costs, increase its output, and gain a critical edge over its competitors. The automation engineer is the key to unlocking this potential. Second is the non-negotiable demand for quality and precision. As we discussed, in industries like pharmaceuticals and aerospace, a tiny error can have devastating consequences. Automation removes the variable of human error. A robot will perform a task the exact same way 10,000 times in a row. This leads to higher quality products, fewer defects, and enhanced safety. It's about building trust with the consumer, whether that consumer is a patient relying on a medication or a passenger flying at 30,000 feet. Third, and this is incredibly important, is worker safety. Many industrial jobs are dangerous, dirty, and physically demanding. They involve lifting heavy objects, handling hazardous chemicals, or working in extreme temperatures. These are the 3D jobs: dirty, dull, and dangerous. Automation allows us to pull human beings out of these harmful environments. Instead of a person risking their health welding in a fume-filled chamber, a robot does the job, controlled and monitored by an engineer from a safe distance. This isn't about replacing humans. It's about elevating them, moving them from physically taxing labor to more cognitive, skilled roles. Finally, there's the data revolution. This is the big one for the future. Modern automated systems are not just dumb machines. They are sophisticated networks packed with sensors collecting vast amounts of data every millisecond. Data on temperature, pressure, speed, vibration, 1,000 other variables. An automation engineer today doesn't just make the machine run. They design the system to harvest this data. This data is digital gold. It can be fed into AI and machine learning algorithms to predict when a machine will fail before it actually breaks, a concept called predictive maintenance. It can be analyzed to find hidden inefficiencies and optimize the entire production process. The automation engineer sits at the critical intersection of the physical world of machines and the digital world of data, making them one of the most valuable players in the age of Industry 4.0. So you have this perfect storm, a universal need across every major industry, driven by the core economic pressures of efficiency, quality, safety, and data. It's a career that places you right at the heart of modern industry, solving the most critical challenges companies face today. The demand is not a trend. It's a fundamental shift in how we make things, move things, and power our world. And with that kind of demand, with that kind of leverage, comes significant financial reward. So what does that actually look like? Just how much can you expect to earn when you possess a skill set this critical? The answer is a big part of why we're talking about this in 2026. Let's cut right to the chase. You want to know the numbers, not vague estimates, not "it depends," You want to see the figures that make this career a serious contender for one of the best in America by 2026. So let's pull back the curtain on compensation. For a brand new automation engineer, fresh out of college with a bachelor's degree in engineering, or someone pivoting into the field with a couple of solid certifications, the starting line is already impressive. We're not talking about minimum wage internships here. In most parts of the country, you can expect to start in the range of $75,000 to $95,000. Yes, as a starting salary. In higher cost of living areas, think tech hubs like Austin, Boston, or Seattle, that number can easily push past $100,000 for your very first job. Compare that to many other four-year degrees where graduates are fighting for $50,000 positions. The difference is stark. From day one, you are valued because the skills you bring are immediately applicable and immediately generate value for the company. You are not a cost center. You are a profit and efficiency driver from the moment you walk in the door. But here's where the story gets really interesting. That starting salary is just the launch pad. The real fireworks happen in the next 3 to 7 years. This is the mid-career acceleration phase. Once you have a few major projects under your belt, once you've proven you can troubleshoot a complex robotic cell at 3 a.m. or write a script that saves 1,000 man-hours a year, your leverage in the job market skyrockets. At this stage, with 3 to 7 years of experience, the national average base salary climbs into the $120,000 to $150,000 range. And that's the average. If you've specialized in a high-demand area like pharmaceutical validation, semiconductor fabrication, or logistics automation for a giant like Amazon or FedEx, you'll be looking at the higher end of that scale and likely beyond. This is the point where you stop just having a job and start having a career. You're not just executing tasks, you're designing systems. You're leading small teams. You're the person they call when $1 million production line goes down. And you are compensated accordingly. The demand for experienced, proven automation engineers is so fierce that companies engage in bidding wars to get them. Now let's talk about the top tier. The senior, principal, and specialist engineers. These are the veterans with a decade or more of experience. They are the architects of entire factory floors, the masterminds behind nationwide distribution networks, the gurus who can integrate a dozen different technologies from a dozen different vendors into one seamless, humming symphony of efficiency. For these individuals, a base salary of $175,000 to $220,000 is standard. But here's the key. At this level, base salary is only part of the story. We need to talk about total compensation. Total compensation, or TC, is your base salary plus your annual bonus, plus any stock options or restricted stock units, known as RSUs. In the world of tech, manufacturing, and logistics, this is how top talent is truly rewarded. A senior automation engineer at a company like Tesla, Google, or Johnson & Johnson might have a base salary of $190,000, but then they get a 15 to 20% annual performance bonus. That's another $35,000. On top of that, they receive a grant of company stock that vests over a few years, which could be worth another $40,000 to $80,000 per year. Suddenly, that $190,000 job is actually a $300,000 a year reality. This is not a fantasy. These are real numbers, pulled from real job offers in 2024, and projected to grow by 2026. This is the level where you're not just building a comfortable life, you're building serious wealth. Think about it like this. Let's imagine a hypothetical engineer we'll call Sarah. Sarah graduates with an electrical engineering degree and takes a job at a food processing plant in Ohio for $82,000, programming PLCs for packaging lines. She spends 3 years there, becoming the go-to expert on their system. A recruiter from a major automotive supplier in Michigan reaches out. With her experience, they offer her $125,000 to help design their new EV battery assembly lines. She excels. After 4 more years, she's a senior engineer. She's seen it all. Now, a new opportunity comes up, this time from a robotics startup in Texas, a company building automated vertical farms. They need someone with deep industrial experience to lead their systems integration team. They offer her a base salary of $170,000, a significant annual bonus, and equity in the company. In 7 years, Sarah has more than doubled her income and acquired a stake in a potentially explosive startup, all because her skills are at the absolute core of modern industry. This financial growth is powered by a few key factors you can control. First, geography still matters. The highest absolute salaries are concentrated in tech and industry hubs: Silicon Valley, Austin, Boston, Seattle, and the Raleigh-Durham Research Triangle. However, The rise of remote work and the boom in manufacturing across the Sun Belt and the Midwest means that incredible, high-paying jobs are no longer confined to the coasts. You can earn an amazing living in states like Texas, Florida, North Carolina, and Ohio, where your powerful salary goes significantly further. Second, your industry is a massive multiplier. An automation engineer at a municipal water treatment plant will have incredible job security, but will likely earn less than an automation engineer working on the bleeding edge of aerospace for SpaceX or Blue Origin. The highest paychecks are typically found in sectors with massive capital investment and razor-thin margins for error. Pharmaceuticals, medical devices, semiconductors, aerospace, and big tech logistics. If you want to maximize your earnings, you follow the money, and right now, the money is pouring into these advanced fields. Finally, your specific skill stack is your ultimate trump card. Being a generalist is great for starting out, but to reach the top tier, you need to be a specialist. Are you the best Rockwell and Siemens PLC programmer in a 3-state radius? That's value. Have you mastered both industrial robotics from FANUC and collaborative robots from Universal Robots? That's more value. Can you combine all of that with Python scripting, database management, and an understanding of cloud platforms like AWS or Azure for pulling industrial data? Now you're not just an engineer. You're an invaluable strategic asset, and your compensation will reflect that. Every one of these high-demand skills you add to your toolkit is like another booster rocket on your career trajectory. And remember, all these numbers are just the direct pay. We haven't even touched on the world-class benefits packages these roles command: fantastic healthcare, generous 401k matching, significant paid time off, and often tuition reimbursement for you to go get that master's degree or that next critical certification, paid for by your employer. The financial picture is clear. This career path offers not just a living, but a pathway to financial independence. The numbers are real, they are achievable, and they are growing. But a huge paycheck is meaningless if you're miserable, burned out, or simply not cut out for the work. The money is the what, but the how and the why are just as important. So, now that we know the potential reward, we have to ask the critical questions. What does it actually take to earn this? What are the non-negotiable skills, the personality traits, and the day-to-day realities of this job that separate the six-figure success stories from the people who wash out? What does a day in the life of an automation engineer really look like beyond the hype? Let's pull back the curtain. Forget the job descriptions and the recruiter speak. Imagine it's 7:45 a.m. on a Tuesday. An automation engineer, let's call her Sarah, walks into a massive manufacturing facility. The air hums with the sound of machinery, a familiar symphony of pneumatics, motors, and conveyors. Her first stop isn't her desk. It's the coffee machine, and then a quick walkthrough of the control room. She's scanning the main HMI, the human-machine interface, a series of screens that act as the central nervous system for the entire plant floor. She's looking for red flags, any overnight alarms or production dips. Today there's a blinking yellow light on line 3, the bottling line. Production efficiency dropped by 7% between 3 a.m. and 4 a.m. Not a shutdown but a bleed. $1,000 an hour bleed. By 8:15 a.m., Sarah is on the floor, laptop in a ruggedized case slung over her shoulder. She's not alone. She's talking to the night shift supervisor and the lead operator on the line. This isn't about looking at code. It's about listening. The operator says, "It's the capper." Every 20th bottle or so, it hesitates, just for a split second, throws off the timing for the labeler down the line. This is where the job splits into two worlds. Sarah plugs her laptop into the PLC, the programmable logic controller, the industrial computer that runs the capper machine. She's now in the digital realm, looking at lines of ladder logic, the language of the machine. She's a digital detective, examining the code that fired at 3:17 a.m. But simultaneously, she's in the physical world. She's watching the machine's mechanical motion. She's listening to the hiss of the pneumatic actuator. She's asking the maintenance technician about the sensor's voltage readings. She is the bridge between the physical and the digital. After an hour of diagnostics, she finds the culprit. It's a combination punch. A pneumatic valve is getting sticky, its response time is a few milliseconds slower than it should be. The PLC code, which is written to perfection, expects a signal back in 50 milliseconds. When it takes 55 milliseconds, the code has a micro hiccup to prevent a crash, causing the hesitation the operator saw. The machine isn't broken and the code isn't wrong. The physical reality has just drifted away from the digital ideal. The fix isn't just to replace the valve. That requires scheduled downtime. The immediate fix, the one that stops the bleeding now, is for Sarah to go into the code and temporarily change the timeout value from 50 to 75 milliseconds. It's a digital band-aid. She documents the change meticulously, then creates a high-priority work order for maintenance to replace the physical valve during the planned shutdown on Saturday. This is the essence of the job. A constant dance between immediate fixes and permanent solutions, between software logic and mechanical reality. It's 10:30 a.m. The fire is out. Now her day shifts. The rest of her morning is spent at her desk, not on the factory floor. She's working on a long-term project, upgrading the facility's entire conveyor system to use variable frequency drives, or VFDs, which will make the lines more energy efficient and give them more precise speed control. This is the engineering part of the title. It involves designing electrical schematics in AutoCAD, programming the new VFDs, and writing a detailed project plan, including budget and timeline, to present to her manager. It's deep focus work. After lunch, the day shifts again. Sarah has a 2-hour meeting with a vendor who is pitching a new robotic palletizing system. Here, she's not just an engineer, she's a business analyst. She's grilling the salesperson on technical specs, integration support, and, most importantly, return on investment. She has to understand not just how the robot works, but how it will save the company money, improve safety, and integrate with their existing network infrastructure. The last hour of her day is about closing loops. She's answering emails, updating the documentation for the Band-Aid she put on line 3. And maybe if she's lucky, she gets 30 minutes of uninterrupted time to learn. She's watching a tutorial on a new machine vision software, or reading about the latest cybersecurity protocols for industrial networks. Because in this field, if you're not learning, you're becoming obsolete. That's a single day. It's a blend of firefighter, detective, architect, and translator. And it reveals that being a successful automation engineer is less about a single skill and more about a specific personality profile. First, you have to be a true systems thinker. A great automation engineer doesn't see a faulty sensor. They see a single point of failure in a complex, interconnected system. They understand that the sensor's data affects the PLC's logic, which controls the motor, which moves the conveyor, which feeds the next machine, which impacts the production schedule, which ultimately affects the company's profitability. They see the entire chain of cause and effect, from a single photon hitting a sensor to a number on a quarterly report. They think in flowcharts and feedback loops. Second, you need to be a calm problem solver. When a multi-million-dollar production line grinds to a halt and a manager is breathing down your neck, panic is not an option. The best in this field have an almost surgical calmness. They have a methodical process. Is it electrical? Is it mechanical? Is it software? They isolate variables. They test hypotheses. They don't guess, they diagnose. They have the MacGyver mindset, the ability to use the tools available to craft a clever solution under immense pressure. Third, you must be insatiably curious. The technology you master today will be a legacy system in 7 years. The programming language, the network protocol, the robot controller, it's all in a constant state of evolution. A degree gets you in the door, but a relentless desire to learn keeps you in the game. The people who succeed are the ones who go home and build a 3D printer in their garage, who read technical manuals for fun, who see a new piece of technology and their first thought is, I wonder how that works. If you don't genuinely love learning about how things tick, you will burn out or fall behind. Fourth, and this might be the most underrated trait, you have to be an empathetic translator. You are the crucial link between worlds that don't speak the same language. You have to listen to an operator describe a weird clunking sound and translate that into a diagnostic strategy. You have to explain to a CFO in plain English why spending $100,000 on a server upgrade will prevent a $200,000 shutdown 6 months from now. You have to write documentation so clear that another engineer at 3 a.m. a year later can understand your code and fix a problem. If you can't communicate effectively to different audiences, your technical brilliance will be trapped in your own head. Finally, you must be meticulously detail-oriented. This isn't a move fast and break things kind of job. In software development, a bug might mean a web page loads slowly. In automation, a single misplaced semicolon in a line of code could cause a 1,000-pound robotic arm to swing into a piece of equipment, causing catastrophic damage and endangering people. One mislabeled wire can lead to days of troubleshooting. One incorrect value in a configuration file can ruin an entire batch of product. You have to have the patience and the discipline to check your work, then check it again. You have to find satisfaction in building something not just that works, but that works reliably, safely, and predictably every single time. So, when you look at the six-figure salaries and the high demand, you have to look past the surface. The reward is high because the required blend of skills is so rare. It's not just about being good with computers or good with machines. It's about being the bridge between them and possessing the unique mindset to handle the pressure that comes with that responsibility. The question is, does that day and does that personality profile sound less like a job and more like a calling? Because for the best automation engineers, that's exactly what it is. And if it feels like a calling, then the next question isn't what do I do tomorrow, but where can this path take me in 10 or even 20 years? This isn't just a job you clock into. It's a career you build, a ladder you climb. And in automation, that ladder doesn't just go up. It branches out in fascinating, lucrative, and powerful directions. For many, the journey begins as a junior automation engineer. Here you're the apprentice, the sponge. You're absorbing everything you can from senior engineers. You're not designing entire systems from scratch, but you're a critical part of the team. You'll be writing and debugging smaller modules of code for PLCs and HMIs, assisting with the installation and commissioning of new equipment on the factory floor, and being the first line of defense for troubleshooting when a sensor goes offline or a robot arm drifts from its programmed path. Your primary goal at this stage is to prove your reliability, your technical aptitude, and your hunger to learn. You succeed by asking smart questions, by meticulously documenting your work, and by demonstrating that you can take a small piece of a massive puzzle and make it work perfectly. After a few years of proving yourself in the trenches, you'll ascend to a mid-level or senior automation engineer. This is where the training wheels come off. The scope of your responsibility explodes. You're no longer just executing tasks, you're architecting solutions. You're handed a problem, not a set of instructions. A business might say, we need to increase the output of this production line by 15% while reducing defects by 5%. It's now your job to conceptualize the entire automation strategy to achieve that. You're selecting the right hardware, the PLCs, the vision systems, the robotic arms. You're designing the control systems and network architecture from the ground up. You're leading the project, managing timelines and budgets, and mentoring the junior engineers who are now where you once were. This is the point where your career truly begins to diverge, where you have to make a choice about what kind of expert you want to become. And this is where the path gets truly exciting. The first major branch is the path of the technical guru, the principal or staff engineer. This is the engineer who falls in love with the technology itself and wants to achieve absolute mastery. They live and breathe ladder logic, they dream in structured text. They have no desire to manage people. Their passion is to dominate the most complex technical challenges the industry can throw at them. This person becomes the company's ultimate weapon. When a multi-million-dollar production line has been down for 12 hours and no one can figure out why, they're the one who gets the call. They can walk into a cacophony of alarms and blinking lights, and with a zen-like calm, diagnose a deeply embedded timing issue in a sub-millisecond control loop that everyone else missed. These are the engineers who become subject matter experts in a specific platform, like Siemens TIA Portal or Rockwell Studio 5000, or in a niche field like high-speed machine vision or collaborative robotics. They don't climb the traditional corporate ladder. They build their own, based on a reputation for being the person who can solve the unsolvable. Their value isn't in managing a team. It's in their unique ability to save a company millions of dollars by solving a single catastrophic problem. The second branch is the path of the leader, the engineering manager or director of operations. This is for the engineer who discovers that their greatest talent isn't just in programming machines, but in orchestrating people and processes. They realize that the principles of automation, efficiency, optimization, feedback loops, and systems thinking apply just as well to managing a team or an entire department. Their focus shifts from writing code to writing budgets, from debugging a PLC to resolving interpersonal conflicts between team members. They're the ones who build the team, who hire the right talent, who set the technical vision for the entire organization. They translate high-level business goals from the C-suite into actionable engineering projects. Their success is no longer measured by the elegance of their code, but by the overall performance of their team, the on-time delivery of projects, and the profitability of their department. This path leads directly into the upper echelons of corporate management, potentially to roles like Vice President of Engineering or even Chief Technology Officer, where they can shape the technological future of an entire company. The third, and perhaps most daring path, is that of the consultant or the entrepreneur. This is the path for the automation engineer who has built a formidable skill set, a strong network, and an appetite for risk. they decide to go it alone. As a consultant, you become a hired gun, a specialist brought in to solve specific, high-stakes problems for a variety of clients. One month you might be designing a control system for a new pharmaceutical manufacturing facility. The next you might be optimizing the robotic logistics for a massive e-commerce warehouse. You trade the security of a single employer for the freedom and potentially massive financial upside of being your own boss. You bill by the hour or by the project, and top-tier automation consultants command rates that can easily rival those of doctors or lawyers. The entrepreneurial route is even bolder. This is the engineer who identifies a recurring problem in the industry and decides to build a product or a company to solve it. Maybe they develop a new piece of software that simplifies SCADA system integration, or they build a specialized robotics integration firm that serves a niche market. This path requires not just world-class engineering skills, but also business acumen, salesmanship, and a relentless drive. It's the highest risk, but it also carries the highest reward, offering the chance to build a legacy and achieve true financial independence. Finally, there's a fourth, increasingly common path: the crossover specialist. The skills you gain in automation are incredibly versatile and are in high demand in adjacent fields. Your deep understanding of how industrial processes work, how data flows through a system, and how to bridge the gap between the physical and digital worlds makes you a perfect candidate for a variety of hybrid roles. You could become a solutions architect, working for a major tech company like Amazon Web Services or Microsoft Azure, helping manufacturing clients integrate their factory floor operations with cloud computing platforms. Or you could become a highly effective sales engineer, traveling the world, using your technical expertise to demonstrate and sell complex automation solutions to other engineers. You speak their language, you understand their pain points, and you have instant credibility. A particularly crucial and growing crossover field is operational technology cybersecurity, or OT security. As factories become more connected, they become more vulnerable to cyber attacks. An automation engineer who also understands cybersecurity is an invaluable asset, tasked with protecting the critical infrastructure that powers our entire economy. So, you see, this isn't a career with a single linear track. It's a launch pad. The skills you develop are foundational, allowing you to pivot and specialize as your interests evolve and as the industry itself changes. But to capitalize on these paths, you must commit to becoming a lifelong learner. The technology of 2026 will be more advanced than today's. The rise of the Industrial Internet of Things, or IIoT, means you'll need to understand networking and cloud data on a deeper level. The integration of artificial intelligence and machine learning onto the factory floor means that the most valuable engineers will be those who can build systems that don't just follow instructions, but that learn, adapt, and optimize themselves. Staying on top means constantly pursuing new certifications, attending industry conferences, and most importantly, maintaining a ravenous curiosity for what comes next. The automation engineer who stops learning is the one who becomes obsolete. The one who embraces the relentless pace of change is the one who will have their pick of these incredible career paths, building a future that is not only stable and lucrative, but profoundly impactful. And that impact, that profound ability to shape the world, is not some far-off dream accessible only to a select few. It's a tangible reality waiting for those with the courage to step onto the path. So, let's stop talking in the abstract and get down to the brass tacks. You've listened this far. You've seen the potential, the salary figures, the sheer scale of the opportunity. The question is no longer, what is this field? The question is now, how do I become a part of it? This is your blueprint, your personal roadmap from where you are right now to a career at the absolute forefront of technological innovation. First, let's talk about the foundation. The traditional route, and for many the most direct, is a bachelor's degree. We're talking mechanical engineering, electrical engineering, or even computer science. These programs give you the bedrock of theory. They teach you the why behind the how, why a certain motor is used, why a particular circuit logic works, why a piece of code is structured the way it is. This is the classical training that opens doors at the largest corporations, the Boeings, the Teslas, the Procter & Gambles of the world. They value that deep theoretical understanding. But let's be crystal clear. The four-year university path is not the only path. The world is changing. A two-year associate's degree in a field like mechatronics, robotics, or industrial automation technology from a good community college can be an absolute rocket ship into this career. These programs are often intensely hands-on. Less time on abstract calculus, more time with your hands on an actual Allen Bradley PLC, wiring a control panel, and troubleshooting a real-world robotic arm. You emerge from these programs as a technician or a specialist, someone who can hit the ground running and be immediately valuable. And in many cases, you can get your employer to pay for you to finish that bachelor's degree later, getting the best of both worlds with zero debt. And then there's the third path, the path of the self-starter, the relentless learner. This is the hardest path, but for the right person, it's absolutely possible. This is the person who lives on platforms like Udemy, Coursera, and YouTube, who buys a cheap PLC starter kit online and spends their weekends learning ladder logic in their garage, who builds a portfolio of personal projects, a 3D printer they automated, a smart home system they built from scratch. This path requires immense discipline, but it shows a level of passion that no degree ever can. Regardless of the path you choose, the educational foundation is just that, a foundation. The real structure is built with specific high-demand skills. This is the toolkit you need to assemble. First and foremost, PLC programming. This is the absolute, non-negotiable cornerstone of automation. PLCs, or programmable logic controllers, are the industrial-grade brains behind almost every automated process. You need to learn ladder logic. It might look archaic like a weird electrical diagram, but it is the language that runs the world's factories. You need to become familiar with the big players. Rockwell Automation's Alan Bradley and Siemens. Knowing how to program in their environments like Studio 5000 or TIA Portal is like knowing how to speak the native language of the industry. Next, you need to understand the physical world. This isn't just about code on a screen. You need a solid grasp of electrical schematics, sensors, actuators, and motors. What's the difference between a proximity sensor and a photoelectric sensor? When do you use a servo motor versus a variable frequency drive? You have to understand how the digital commands you write translate into physical motion and action. This is where the engineering part truly comes alive. Then we layer on robotics. The world isn't just being automated, it's being robotized. You need to get familiar with the major industrial robot manufacturers Fanuc, KUKA, ABB. Understand robot kinematics, coordinate systems, and safety integration. You don't need to be a PhD in robotics, but you need to be comfortable teaching a robot a new path, integrating it into a work cell, and understanding how it communicates with the rest of the system. Now, let's add the next level of sophistication: HMI and SCADA development. HMI stands for Human-Machine Interface. It's the screen the operator uses to interact with the machine. SCADA, Supervisory Control and Data Acquisition, is the bigger picture, the control room system that oversees the entire plant or process. Learning platforms like Ignition or Wonderware allows you to create the intuitive, graphical interfaces that make complex systems usable. This skill alone can make you incredibly valuable, as it bridges the gap between the complex machinery and the people who run it. And finally, to truly future-proof your career, you need to embrace the IT and data side of automation. This means learning a text-based programming language, with Python being the undisputed king. Python is the glue that connects the industrial world to the data world. You can use it to pull production data from a PLC, analyze it for inefficiencies, and even integrate machine learning models to predict maintenance needs. You also need to understand industrial networking. How do all these devices talk to each other? You need to know about protocols like Ethernet/IP, Profinet, and Modbus. This convergence of operational technology, OT, and information technology, IT, is where the most exciting and highest-paying opportunities are emerging. So, you have the foundation, you have the toolkit. What's missing? It's the polish. These are the soft skills that separate a good engineer from a great one. Communication is at the top of the list. You have to be able to explain a complex technical problem to a non-technical manager. You have to be able to listen to a machine operator to understand what's really going wrong on the floor. Project management is another. You'll be leading projects from conception to completion, managing budgets, timelines, and vendors. And most importantly, you need a relentless curiosity and a problem-solving mindset. Every day is a new puzzle. The machine that worked perfectly yesterday is alarming out today. Why? You have to be the detective, the troubleshooter, the person who enjoys the challenge of figuring it out. So we circle back to the central question of this entire video. Is automation engineering a top career choice in the USA for 2026? Let's look at the evidence. We have a field with a median salary pushing, and in many cases soaring past 6 figures. We have a massive and growing skills gap, meaning demand for your talents will be incredibly high, granting you unprecedented job security. We have a career that spans every conceivable industry, from building electric cars to making life-saving medicines, giving you the freedom to follow your passions. It's a career that is inherently future-proof, because you are the one building the future. It's a job that challenges you intellectually every single day, blending hands-on work with high-level thinking. So the answer is an unequivocal, resounding yes. But it comes with a condition. It's a top career choice for a certain type of person. It's for the perpetual student. It's for the problem solver. It's for the person who sees a complex, broken system not as a frustration, but as an opportunity. It's for the builder, the creator, the innovator. If you have watched this far, chances are that person is you. You feel that spark, that curiosity, that desire to build something real, something that matters. So don't let this just be another video you watched. Let this be the moment your trajectory changes. Your call to action isn't to like or subscribe. Your call to action is to open another tab right now. Search for PLC Basics tutorial. Search for your local community college's mechatronics program. Search for Python for automation. Take one small concrete step. Today, not tomorrow. The future isn't waiting for you to be ready. The future is being built right now in factories, warehouses, and labs across the country. The only remaining question is whether you will be one of the architects. The choice is yours. Make it.